Hey there guys, Mr. Carlson here. Let's do an example problem with friction. So right here we have a 50 kilogram block and we are going to pull it to the right with some amount of force. They tell us in this problem that the coefficient of static friction between the block and the ground is 0.3 and that the coefficient of kinetic friction is 0.1 between these two surfaces. So we've got mu for static and kinetic friction, and we've got the mass of the block. So we've got three questions here. Part A is what force applied would we need to get the block just moving? So it's starting from rest. What force applied do we need to apply to that to at least get it moving? So we're going to get back our equation here. Force of friction is going to be equal to mu times the normal force. So pretty simple for this first part. The force applied here to get it moving, well, my force applied is going to have to at least match, to get it moving, it's going to have to match, at the very least, that force of static friction, right? And so force applied then is going to be equal to that force of static friction to get it moving. And so really what I'm solving for is the force of static friction, which is going to be equal to that mu of static friction times the normal force. So our mu of static friction is 0.3. And we're going to multiply that by the normal force. Well, the normal force, we know, is going to have to be equal to this force of gravity here. So in this case, let's see, we'll just make it easy. We'll multiply this. Instead of 9.8, we'll just say, we'll round it up to 10. So 10 times 50 means that that force of gravity is going to be somewhere close to 500 newtons. It's probably going to be a little less than that, but we're not using 9.8 in this case. So that means my normal force here is going to be equal to that. It's going to be 500 newtons as well. And so that's what I'm going to plug in right here, 500 newtons. And so let's see, 500 times 0.3, let me plug that into my calculator real quick, is going to be 150. So that means that your force applied just to get the block moving would have to be at least 150 newtons. Because 150 newtons is the force of static friction pulling this way, so that means your force applied would at the very least have to be 150 newtons, probably a little more than that, but that's going to be the minimum to get the block at least broke free from that force of static friction, broke free from that, and then it would get the block moving. Then for part B, what force applied then after we break it free, what force applied will we need to keep it moving at a constant velocity? Well, we already know this, that for a constant velocity, for anything to be moving at a constant velocity, the forces have to be balanced. So that means in that case, once it's moving, the force applied is going to have to be equal to the force of kinetic friction in that case. So for part B, my force applied needs to be equal to the kinetic friction pulling back. So I need to solve for that in this case. So the force of kinetic friction is going to be equal to the mu of kinetic friction times the normal force. So in this case, it's just going to be 0.1. So kinetic friction 0.1 times that normal force of 500 newtons. And so that means I would only have to apply 50 newtons of force. So once it breaks free, I apply that first initial 150 newtons to break it free. Then I could actually pull with less force, quite a bit less force, 50 newtons, just to keep it moving then at a constant velocity would be just 50 newtons. Then the final part here, what force applied would we need to accelerate it now at 3 meters per second squared? So now instead of moving it at a constant velocity, I want to speed it up at a rate of 3 meters per second squared. Well, we've already talked about this as well when we were talking about Newton's second law. Whenever we want to accelerate something, the forces need to be unbalanced. So if I want it to accelerate to the right, that means now my force applied is going to have to be greater than whatever that force of kinetic friction is. So in this case, to accelerate it at 3 meters per second squared, this is going to have to be more than whatever this is. Now I need to figure out how much more though, right? And this is where Newton's second law comes in. So remember Newton's second law, the net force is equal to the mass times the acceleration. Well, we know this is the rate that we want to accelerate it, and we have the mass of the block. It's 50 kilograms. So I can use those two things to figure out what's the net force, the total amount of force that I would need to do that. So let's plug that in down here. So acceleration, whoops, not acceleration. Why did I write it like that? We're solving for net force. So net force is going to be equal to the mass, 50 kilograms, times the acceleration, which is 3 meters per second squared. So we're going to get 150 newtons. Now, be careful. So that's not your final answer. That's not going to be, oh, it's just, I need to be 150 newtons, right? It's not going to be that, because that 150 newtons, that's the net. That's the total, basically, after this and this are kind of added together. And what we're left over with, that's going to be the net force. So really what I need to think about is right here. We need to think about the fact that the net force in this scenario, the total force, is going to be equal to FA. And then I'm going to put minus the force of kinetic friction, right? So this, subtracting off this from this, whatever I'm left over with is the net force. Well, the net force we know is 100, I'll write it down here, 150 newtons. That's what I need to be left over with. And the force applied, well, that's what I'm trying to figure out. I don't know what that is. And the force of kinetic friction, well, we just did that in the previous problem, right? The force of kinetic friction is 50 newtons. And so now I can see that I can solve for my force applied, which would just end up being 200 newtons. So the force applied to accelerate it would be 200 newtons. And that makes sense, because if I were to pull this way with 200 newtons and my force of kinetic friction pulling back is 50 newtons, that means I'd be left over with 150, which is what I need to accelerate it at that 3 meters per second squared.